try not to say
Some people don't like it because they have secret results.
Oh.
Yeah. Hey, thanks everybody for coming. We have a very special visitor today, Joan Najita, who is from NOAO, our sister institution, NOAO, soon to be even closer related, potentially.
Theoretically.
Theoretically. Okay. Descent from the back of the room. So Joan did her PhD at Berkeley, and then she was a postdoc at Space Telescope for a while. Even though she was saying that she was a theorist, they hired her to do instrument work when she was a theorist, which they must have been really desperate for infrared people at her time. And then she's been at NOAO since then. So she's going to talk to us today about a wide variety of topics.
All beginning with us.
Yeah, there you go.
Okay, thanks very much. Yeah, so everybody, thanks so much for coming and for the invitation to visit. And it's really great to be here, and I'm hoping that we'll have a chance to chat more about things of mutual interest, both science and observatory operations or any other observatory service related things in anticipation of our upcoming merger. So it'd be nice for the science staffs to be able to do some things collaboratively as one of the advantages of that whole thing. So I hope we'll have some chance to chat about that. But anyway, for today, I was hoping to, well, thank you for the opportunity to share some science thoughts. So often when, you know, you are, as a busy observatory professional, you may wonder, is my science really going anywhere? Do I have enough time to be doing that? And is my field really advancing? And so often when you're in that state, if you ever have been in that state, it's a really good idea to take a big 1 or 2 steps back and maybe think about how your field has been changing over time. And so I did this a couple months ago in preparation for a meeting that Trent and I went to. And I argued there that actually, when you think about it, even though personally my progress may be seeming kind of slow, we're actually living in a golden age of star and planet formation. And one way that we can think about that is by considering what things used to be like in the old days, like when I was a grad student. So in the old days, this is what we had for star and planet formation. I don't know if anybody remembers the old days, but it had many of the right elements. There were lumps in molecular cloud cores. It was black and white in those days. And these cloud cores get denser and denser, they eventually collapse, and material rains down onto a star and a disk. You know, molecular clouds, you have angular momentum, so you can't just make a star, but the excess angular momentum goes into orbit around the star and disk. Eventually, the star launches a wind, and that blows away most of the infall, leaving behind a fried egg. And notice that in this picture, there's no planets in the picture. And that's because in these old days, we were pretty busy thinking about some other things, like, do disks exist? There are stars out there. What determines their masses? And if we had a little extra time, we would also try to think about, well, could there be planets around other stars? So as you can see, things have changed. Hey, pretty amazing. We now live in a time of amazing wealth. We have tremendous observing resources on the ground and in space. We have tremendous computing resources and fantastic theoretical ideas. And as a result, we've made a lot of interesting discoveries. So in answer to the question of whether planets exist, I think we can say yes. And there are a lot of them, maybe even 100 billion or more, every one of them unique. And indeed, you know, you're probably all familiar with what these exoplanet distributions look like, but when you look at them in terms of the mass or the orbital separation, they come in all flavors, every possible kind you might want to have, and all quite different, different in addition, in comparison to our own solar system, which tells us something interesting. We can use these demographics of planets to give us some insights into how they form. So for example, the fact that many planets are a lot closer to their central stars than the planets in our own solar system suggests that orbital migration, planets might form at large radii and migrate in closer to their stars. what other kinds of clues do these exoplanet distributions offer? Let's check that out. Another question is that we have made a lot of progress on is the question of, do disks exist? I think we can say yes. In the old days, we had these kinds of diagrams. And so when Hubble Space Telescope turned its eye toward the Orion Nebula, we were thrilled to find that, yes, there are things in nature that look a lot like our fried eggs. Hooray. Well, things have really advanced since then. Thank goodness. It's been a couple decades. And now when we look at disks with high contrast imaging, we see something amazing. They're not just fried eggs, very smooth fried eggs or anything. They have a lot of structure that we didn't anticipate. So this is kind of amazing because ALMA came online not too many years ago and immediately made its best image ever. And yes, it's amazing. It was really different from what we expected. But it's not the only image, and observations in the millimeter both before and since have also been amazing, producing interesting structure like these kinds of millimeter disks that don't have any emission in the middle, things with holes or cavities. Sometimes there's emission that looks like lobes. There are these rings and sometimes even spirals. So what are these interesting structures telling us about planets? Are these the fingerprints of planets or something else? If they are due to planets, what kind of planets are they? How many are there? Where are they located? And the fact that we've seen these kinds of structures, what does that all say about planet formation? These are the kinds of questions that people in Star Planet Formation are wrestling with, and multitudes of papers are being written. So how do planets form? Back in the Tin Age, the old days, we had a lot of diagrams and ideas and some pretty good stories. So the story of core accretion is that it's a bottom-up process. You start from small micron-sized grains. These collide and stick together and grow magically into kilometer-sized planetesimals. These kilometer, neighborhood-sized rocks stick together and grow into protoplanets, thousands of kilometers in size, which could collide and grow into the cores of giant planets, maybe 5 to 10 Earth masses in size. And these could accrete gaseous envelopes and make giant planets. So it's a great picture because it explains why we could have terrestrial planets and giant planets in the same system, like our own solar system. And it can explain why we might see rocky planets and gas giants around other stars. But even in the old days, in the Tin Age, we had some reservations about this picture. So one reservation was, does this really work? It's kind of hard to go from micron-sized things up to planets, right? And if you're a micron-sized grain, things pretty good because you're well coupled to the gas, and so as the gas spirals in, you're spiraling in, pretty safe. But when you get to a kilometer-sized, and when you get to a kilometer-sized planetesimal, that's also good because there you don't even notice the gas. You can just go around in your Keplerian orbit, and you're also safe. But if you're in the danger zone, this intermediate size here, which would be a meter size at a distance of an AU, life's not good because you're going in trying to go at Keplerian speed, and the gas is going a little bit slower, so you see a giant headwind, and that causes you to lose angular momentum and spiral into the star ahead of the gas. And you spiral really fast. In a mass solar nebula, you travel that last AU in only 100 years, so a tiny fraction of the lifetime of a disk. And so if this really happened, this would be a really great way to deplete your entire disk of all your planet building material. No planets, not good. Well, in addition to this classic problem of planet formation, there was another problem that was identified by laboratory astrophysics. And it's basically that, when you think about it, you're starting from micron-sized grains and trying to stick them together to grow something pretty big. And you're relying on van der Waals forces. That's tricky. Van der Waals forces are not very strong. And it turns out from elaborate laboratory experiments that it's really hard to get beyond a centimeter size. So the classic picture of sticking things together to make things grow is a real problem, both at the centimeter size and at the meter size. Well, luckily, in the intervening years, theorists are very clever and they've come up with all kinds of ideas to help us solve this problem. People think that ices are more sticky. They could potentially cause things to grow more quickly and accelerate the formation of bigger objects. There could be interesting dynamical processes like the streaming instability that can concentrate solids more quickly and cause them to gravitationally collapse. Many ideas to solve this problem. But I think we still want to know, from an observational point of view, here we are at Gemini Observatory, still want to know from an observational point of view, does this picture really work? Does the core accretion model really build these planetesimals and protoplanets? So how can we investigate that? So today, I wanted to cover a couple of questions related to all these ideas that I've just mentioned. So one question is, can we probe this earliest, most mysterious phase of planet formation and see whether disks are really forming planetesimals and protoplanets? Can we look at these distributions of exoplanets and learn something pretty basic about planet formation, like the time scale and efficiency of planet formation? These kinds of images that we've been seeing here of rings and spirals and disks, are they signposts of planet formation or something else? And then if we have a little bit of time, I wanted to try to cover this bonus topic, which goes back to an oldie but goodie question from star formation, which is that we've been saying that material spirals in from the outer disk to the inner disk, eventually making its way onto the star. But how does it do that? What is the mechanism that drives disk accretion? Let's see if we can come up with some new insights into that old question. Okay, so let's start with the second one. Can we look at the exoplanet distribution and learn something about some basic stuff about the formation of the timescale and efficiency of planet formation? And here I want to just make a simple comparison by comparing the solids that are locked up in these exoplanet distributions with the stuff that they formed from the solids that are in disks. So let's look at the very end point of this process, count up the solids that are there, and look at the very initial process, the initial phase of this process, count up the solids that are there, and see what it can tell us about how that process works. It should be simple because we know a lot about exoplanets and we know a lot about disks. And with disks, we're always measuring the solids anyway. So that seems like the right thing to compare. Okay, so let's work on the exoplanets first. You're all familiar with these kinds of diagrams that show that planets are detected through transits within an AU. They're detected by radial velocities, by microlensing, somewhere between 1 and 10 AU, and also by direct imaging. But we haven't detected very many direct imaging planets yet, so let's just use debris disks as an alternative tracer because they also probe this larger separation distance. Okay, so here are our 3 bins. Inner, within an AU, middle, 1 to 10, and outer, 10 to 100. Okay, let's count it up. And here, when we do our counting, we only want to count the solids. So forget about the gaseous envelope part, we just count the solids. And of course, we want to correct for detection efficiency. When we look here, we're just seeing the planets that were actually detected, but we want to know what is the true underlying distribution from which they're detected. Like hot Jupiters are easy to see, but they're not most of the population because they're just easy to detect. So we want to correct for the detection efficiency of those things. And luckily, people actually report that, so we don't have to do that step ourselves. We can just add it up. Okay, so let's add it up. So in the region, within an AU, this is the cumulative distribution from Kepler, and it says that about 50% of all systems within an AU have about 5 Earth masses and solids. The next bin, from 1 to 10 AU, which is probed by microlensing, is pretty interesting. It says that about 60% of systems have a super Earth, so that's 5 Earth masses of solids. About 50% of systems have a Neptune, which is 10 Earth masses and solids. It's really adding up, it's quite a lot. And then 20% have a giant planet. That's another 10 Earth masses. Okay, then let's go to the last bin, the very outer bin. About 20% of stars have debris disks, and those are produced by something like 10 to 100 Earth masses of solids. So now, we have our 3 candy jars, the inner AU, the 1 to 10 AU region, and the outer region, and we can, Monte Carlo, grab a bit of each to make up synthetic planet distributions. So, yeah.
How do you know the solid contribution in Neptune? How do you know?
That's a good question. That's a good question. So with microlensing, you can measure the mass of the planet. And let's say it turns out to be the mass of Neptune. Then we have to infer what kind, for like Neptune in our solar system has a core that's 5 to 10 Earth masses, so, or maybe 10 to whatever. So something of that order would be the way to do that. I mean, it's not exact. We would really like to have a better accounting, but roughly speaking, that would be a sensible thing if we didn't have further information. Okay. All right, so now we've got our 3 bins and our rough rates, and so we can make some synthetic distributions. And so this is the answer in the green. So 50% of all sun-like stars have about 20 Earth masses locked up in exoplanets. And 80% of sun-like stars have about 10 Earth masses in solids. Okay, so that's quite a bit. And now let's compare them to the disks. Now, to do that, we have to figure out which disks should we compare to. So we need to look at the different kinds of disks from which, as part of the star formation process. And you know, the classic thing is that there's class 0, 1, 2, and 3, which are just pictures of a star growing up. Okay, so class 0, there's not much of a disk. The star is just growing its mass. In the class 1, the star is still growing its mass, but it's now gotten rid of some of the infalling stuff. In class 2, it's totally gotten rid of the infalling stuff, and it's a star and a disk. And in the class 3 phase, it's a disk. I mean, it's a star. Okay, so we said, in the tin age, what is the primordial disk that I should compare my planet mass function, my planet solids to? People would have said, here, you should be looking here. Okay, so let's check that out. So if this is the exoplanet, the solids in exoplanets, the black curve is the solids in the class 2 disks. And you can see that the most massive disks have more mass than the exoplanets. So that's great. They could potentially be the disks from which planets are being built. But the lowest mass disks have less mass than the exoplanets. So they could not be the disks from which planets are being built. What does that mean? Well, if we think that the disks around Tauri stars are the disks from which planets are being built, that probably says that solids have grown bigger in size than millimeter observations can measure. They can only measure things up to a millimeter or a centimeter, whereas if planet formation is going on, solids would have grown to much bigger sizes. So could it be that the Tauri stars are not the right disks to look at, and we should really be looking at a younger population, the class 1 disks? If this is right, they will have more mass than all the exoplanets. So let's check that out. Aha, class 1 disks do have more mass than the exoplanets. So at least some population has enough mass. So that's great. But you notice that it doesn't have all that much mass. It has 3 times the mass, roughly, of the exoplanets. If you went from here to here, it's about a factor of 3. So that's actually pretty interesting. These comparisons suggest something pretty simple, but I think pretty basic about planet formation, that it's really efficient and it begins really early. So if those class 1 disks are the primordial disks from which exoplanets form, those disks are pretty busy. Some of the material is spiraling in, making its way onto the star. Some of the material is being injected into a wind. And even with all that, 30% of all the solids are somehow going into the exoplanet populations that we already know about. If we find lots more exoplanets, that'll mean planet formation is that much more efficient. So it's pretty tough, I think, to challenge, I think, to exoplanet formation theories to explain how planet formation can be so efficient. And planet formation also seems to begin a lot earlier than we thought. It's not Tauri disks. They're not the disks from which planets are about to begin forming. They're very well evolved, and it's really a much younger kind of star, the class 1 disks, that's when planet formation begins. So in other words, if you say, I think in the old days, in the tin age, people would say, you build the star first, Then you start making planets. No, you actually start building your planets while you're building the star. It's a story of two interwoven processes, star formation and planet formation together.
You could say that the closer in planets start in the earlier stage and the later ones do not have to.
That's
Because the
possible.
Tauri disk can support go further planets away. So
That's true. Most of the mass that we know of is in that intermediate region, in the 1 to 10 AU region. So
okay, and that's where the
Yeah.
Tauri starts to.
in terms of total.
Yeah.
All right, so learned something interesting there. Clearly, Tauri disks are not up here. They've grown their solids into something bigger than millimeter observations can measure. How big did they get? Okay, so let's get to the second topic. I mean, the very earliest, most mysterious phase of planet formation. And as we mentioned, theorists are hoping that they have some answers to how this all works, but ultimately we want to know, do these building blocks of planets, the icy planetesimals, do they really form in disks? Now, to know that, we have to know what is a planetesimal. Here's an example of a planetesimal, a comet. It's icy and it's a kilometer in size. Great. We also recently had another look at another kind of planetesimal, a visitor from another solar system. Awesome. And sometimes when disks have a lot of leftover planetesimals around, they collide and crush themselves down into tiny grains that we can see in the reprocessed light from the central star. So these debris disks are also signatures of leftover planetesimals. But they're planetesimals from long ago, like long after the planet formation process has ended. And what we really want to know is not whether there ever was a planetesimal. We want to know that when in the planet forming era, do planetesimals form early enough in this phase and abundantly enough to actually be the building blocks of planets? Now, one option would be to try to look at an image like this, the best image we've ever had of a disk, and see whether there are any planetesimals there. But that's going to be a little challenging. So let's try something, but let's be a little more creative there to try to find a planetesimal, a kilometer size, a neighborhood size rock within a disk. How can we find that? Let's try something else, chemistry. Okay, so this part is like the worst diagram in my entire talk, so just bear with me. I'll try to go through it pretty simply, but I think it makes sense. Okay, so let's say we wanted to do this challenging thing of trying to find rocks, big rocks in disks. How would we do that? Say this is the snow line here, and we're looking at this icy region over here. And let's say that we're going to make kilometer size and 1,000 kilometer size planetesimals and protoplanets. And as I mentioned before, those guys are pretty lucky because they passed the danger zone, and now they're big enough that gas drag doesn't play a role. So they can just park on their Keplerian orbits. So this is great because if you were able to make these rocks, that they are now holding on to all the water and oxygen that they're made of, they're not going to migrate in any further. And that means that the material that migrates into the inner region through accretion is going to become increasingly carbon rich because you're starving this region of all the oxygen. And that has a particular chemical signature. As you go to an increasingly carbon rich environment, you produce a lot of hydrocarbons and you'll have very little residual oxygen left over. So your water abundance will go down and the ratio of hydrocarbons to water will rise with maybe a factor of 2 change in the C/O ratio, increasing the ratio of the hydrocarbons to water by a factor of 10. So it's a really big signature that one might predict. And you might say, if I have a more massive disk, I'll be further along in this process. I'm going to produce more planetesimals and protoplanets, and I'll see a stronger chemical signature. Okay, so let's see. Do we see a signature like that? So it turns out from the data that we collected in the Spitzer area, the answer is yes. So if we look at the flux of an organic molecule like hydrogen cyanide, ratio to the flux of a molecule like water, and compare it against disk mass, we see an actual trend. It's kind of weird because this ratio is coming from this region of the disk within the snow line, and this disk mass is probing the region way out here. So why should they be related? I think it's because something interesting is going on in the intermediate region where giant planetesimals and protoplanets have formed and sucked up all the oxygen from the inner disk, producing this kind of trend. They may say, well, that's a really far-fetched idea. You don't even know that the HCN and the water are really coming from the same region of the disk. And indeed, that's true because with Spitzer, it's spatially and spectrally unresolved. But luckily, Gemini is an amazing telescope, and it works so amazingly in the mid-infrared. So with TEXIS on Gemini, we're able to measure line profiles of the water and the HCN. Here they are in an example disk. And they're beautiful profiles, and they're very similar. So that says that the HCN and the water that we're measuring here come from the same region of the disk, and it makes sense to use them as a tracer of the C/O ratio in the inner disk. So this trend suggests that most disks, it's not just one disk, but most disks are participating in oxygen sequestration beyond the snowline because they formed planetesimals and protoplanets. In other words, disk chemistry is giving us an important clue to the question we asked earlier. Tauri disks are not up here because they've grown their solids into bigger sizes. How big did they grow? Not just a little bit bigger, but probably quite big, large enough that the bodies have stopped migrating, so planetesimals and protoplanet sizes. Now, this maybe has something interesting to say about a really popular topic in star and planet formation today. What's going on about these rings in disks that we hear so much of? So you probably remember seeing this, that ALMA observed HL Tau has lots of rings here, and the rings are on the same size scale as the planets in our solar system, highly suggestive. And as I mentioned before, these sorts of rings are very common. So here's a couple other examples of systems with rings. Now, the very earliest interpretations of what we're seeing here is that each ring is a footprint of a planet. So a planet is there, and it pushes away the gas and dust in the vicinity of its orbit, making this dark ring. So I see a lot of rings here, so the interpretation is that there's a lot of planets there. Really? So some recent work by Robin Dong and some other folks show that it's possible to create some of the same structures with many fewer planets. So here's a look at the gas and the dust in a disk at early times and later and later. And in this simulation, there's just a green dot right there, right there, right there. So there's one planet producing these multiple rings in the millimeter observations. So one potential interpretation is that we see many planets, or maybe one planet. And another interpretation is that we see no planets, that the structure that we're seeing here is just an effect of grain growth. So could it be, this is just another paper in the literature, could it be that many of these rings are the effects of snowlines, where icy grains crossing the snow line dump their water into the vapor phase, and this condenses back across the snow line, fueling the growth of increasingly large sizes of solids. And say those solids grow to something like 10 centimeters in size, that's big enough that these rings would become optically thin in the millimeters. So the reason why, so this interpretation, the reason why we see rings is not because there are any planets there, but just that there's a total lack of opacity due to very large grain growth. So these different interpretations here say different things about the state of planet formation. The snowline interpretation is that we're way up here in the planet formation story, and maybe we've grown to 10 centimeter sizes. Whereas the other interpretation suggests that we're really down here, that you've already formed a 10 Earth mass planet or larger. So which is it? This is a really active area of research now, people trying to address this with many different techniques. But I'm thinking based on what we just heard earlier, that the results are probably going to suggest that the answer is going to be much further down here, because as we were saying, there's chemical evidence for the formation of very large objects. So the jury's still out, but I'm thinking that this is probably how it'll go. And it's possible that the Snowlines, as we mentioned very earlier, could actually help jumpstart the process of building these larger solids. So it's not that it's just one or the other. Many different processes could play a role, but most likely, most Tauri disks are farther down here, toward the end of the story. Okay. So what about moving on then to another kind of structure that's seen in disks, disk spirals. So as we've been discussing, these kinds of rings are often seen, but also spirals. And spirals are also seen in scattered light images, so high contrast near infrared images. So here we've got some two-arm spirals seen here. And there are also multi-arm spirals in here. And this might be a single arm spiral. So when you see a paper about these kinds of results, people often tell you a lot about this source, or about this source, or about that one. But my collaborators and I were kind of interested, so Robin Dong and Sean Britton, we're curious to see what we could learn about the nature of these kinds of spirals by looking at them as an ensemble altogether. Okay, so taking a look at just the top one, the two-arm spirals. So here are the two-arm spirals. If we look at the parent population from which these detections are made, it turns out that the parent population is very small. So out of the young intermediate mass stars that have been studied, these two are detected as spirals, but only 10 of them have actually been studied in a similar way. So there are 10 Herbig stars, stars with masses greater than 1.5 solar masses, that have been well studied in scattered light, that are near and young. So that's a really high detection rate. 20%, I mean, just literally if you use the numbers, 20% of stars have spirals. What could they be due to? Well, there are two possible explanations for these spirals. One is that they're due to a massive planet, 5 to 13 Jupiter masses, far from the star, 30 to 300 AU. So if you see a spiral like this, it points to the planet there. Another possible interpretation is that it's due to a gravitationally unstable disk. And if you have two arms like this, this is a very gravitationally unstable disk. The disk mass might be half the mass of the star, so huge. You know, if you have a disk that's that massive, it's highly unstable, and instability is trying to drive it out of that phase as quickly as possible. So you don't expect to see a disk in this phase for very long. It's expected to be a very brief phase of planet formation. So that seems to be an unlikely explanation for a phenomenon that's seen 20% of the time. So the best interpretation of this kind of spiral structure is actually a planet. And these sorts of planets should be really easy to see, right? They're massive, 5 to 13 Jupiter masses, and they're far away, 30 to 300 AU. That's the best kind for direct high contrast imaging detection. So it's interesting, when people look at these systems to look for planets, they don't see them. So you might think, maybe the spiral arms are messing us up. You know, the spiral arms are really bright. They make it harder for us to see the planet, and maybe we don't really know how bright the planet is supposed to be. Instead of trying to detect the planet in this system, why don't we just wait a while, look at an older system after the spiral arms have gone away, and then see if we can detect the planet. Okay, so people have been doing that. So when people look at mature stars older than 10 million years of the same mass and try to detect these planets, the detections are made in fewer than 3% of systems. Kind of strange. Here we have a phenomenon that's detected 20% of the time, but the planet that should be driving it is detected very infrequently. What could that be due to? Well, I think the most likely explanation for that is that planets are a lot fainter than we've been thinking. So when people say I have a 3% detection rate or whatever, that's based on a certain kind of planet that they're translating their detection limit into a mass, so-called hot star planets. But planets are probably not actually born hot stars. So if we look at this old paper by Fortney et al., it shows that hot star planets, that's these dotted lines, are born bigger, hotter, and more luminous than the cold star planets. But we actually expect planets to be born cold because that's a prediction of core accretion theory. Core accretion theory predicts that as the planet is gaining mass, say material is falling onto it, it radiates away most of its energy in a shock. So the hot star model is that the accretion energy from which a planet forms is included in the object, so it remains luminous and hot and large for a longer period of time, making it easier to detect. In cold star, it's active dynamical accretion onto the planet, which radiates a lot of the luminosity through the accretion process, so the resulting object is colder, smaller, and less luminous. So I suspect that the reason why many planet detection programs have not detected massive planets to her big mass stars is because those planets are much less luminous. We need to go fainter, maybe an order of magnitude fainter in luminosity in order to detect them. So for example, let's say we're looking for a 10 Jupiter mass planet at a billion year, or no, 10 to the 100 million years. Okay, hot start would predict that it's 10 to the -5 solar luminosities, whereas cold start would say it's more like 10 to the -6. So we need to look a lot harder if we want to see those planets. But you might have already seen that this is kind of a weird situation here because we're not detecting planets anywhere. Okay, we're not detecting planets at late stages because they radiated away all their energy early. We should be able to detect them when they're young because that's when they're radiating away all their energy, right? So it's quite interesting that we've really only made 2 detections of accreting planets in all the time that we've been looking. I think that's right, Trip. So Lit calcium-15, where we detect a couple of objects there. One might have H-alpha emission. There's also recent detection of PDS-70 there, which also has H-alpha emission. So where is the luminosity of the formation of planets? From a core accretion perspective, we do expect to see them early on, but we're not seeing them. And the fact that we don't detect them at late times, I think is a matter of not going deep enough. So it's a really interesting question, and maybe Gemini will play a role in solving this problem. I'm not sure. Okay, so I guess we do have time to, lots of time, to study this last topic on disk sizes. Okay, so this is an oldie but goodie. Stars are supposed to build up their masses by material spiraling in from the outer disk, eventually making its way onto the star. How do they do that? As they're spiraling in, they may also drag in giant planets with them. So accretion is expected to be important for the formation of the star. It may also be important for the architectures of giant planets. How does this process actually work? So 25 years ago, people were really thrilled to rediscover this thing called the magnetorotational instability, okay, which was supposed to save the day, explain how this all works. The way that works is that you have weak magnetic fields threading a disk. And let's say we have a magnetic field line like this, and I have 2 blobs on it, and I just displace them. The one that moves in will tend to go faster, and the one that moves out tends to go slower. And the rubber band, that's the magnetic field, will try to pull them back. This causes the inner one to lose angular momentum, and this one to gain angular momentum, so they want to go further apart. That's the nature of the instability. And so if you do a big simulation, you find that it generates MHD turbulence, like that. And the ultimate result is that a small fraction of the mass acquires most of the angular momentum, which allows the rest to accrete. And so that's the accretion process. Now, this clearly is only going to work, it's a magnetic field, so it's only going to work if the disk is ionized enough to grab on to the magnetic field lines. And this is the big problem for disks, because they're really thick, and they're only ionized by very weak ionizing sources like stellar X-rays. So disks traditionally will have trouble doing this. And as time has gone on, it's just become worse and worse and more embarrassing. Because observationally, we've learned more and more about accretion. As material crashes onto the central star, we measure that luminosity and infer how much mass is falling down. And it appears to be growing with stellar mass. So accretion rate grows with stellar mass. It declines with time, but we really don't know how that works. As theorists look closely into the non-ideal MHD processes that affect exactly how the magnetorotational instability can work in disks, it seems harder and harder to make this work. And so I went to a meeting at the Copley Institute for Theoretical Physics where all the theorists were saying, nope, can't do it. Nope, can't do it. I'm just giving up. Nope, that's just not going to work. And so the hot new idea of the day is something called disk winds. It's actually an old idea, but everybody's really enthusiastic about it now. Okay, so the idea is that we're abandoning the idea that the disk can solve its own angular momentum by redistributing angular momentum in the disk. And we're invoking something else, disk winds, to just remove the angular momentum from the disk in order to allow accretion to occur. Now, you might be a little suspicious of that picture. So let's see, before we throw the baby out with the bathwater, whether there's some observation that we might be able to make to test these two ideas. So if the disk is solving its own angular momentum problem, the way angular momentum redistribution works is that some amount of mass acquires most of the angular momentum and moves to larger radii, while the rest accretes. So that means that disk will spread with time and get bigger. If winds are removing the angular momentum, then they remove the angular momentum and drive a torque in the disk, which causes angular momentum to causes material to accrete onto the star. So in fact, the angular momentum is just being removed right from the disk, so the disk does not need to spread and it could shrink. Now there are other processes that could also affect the size of the disk, and they all tend to make the disk smaller. Photoevaporation can remove material from the outer region of the disk, and if you had stars or planets that form out here, they could also truncate the disk. So you have numerous ways to make the disk smaller, but only disk spreading in disk angular momentum transport can make the disk bigger. So if we could measure the sizes of disks, which have been measured actually, and we're looking at gas disks now, and measure the sizes of disks over time, say compare class 2 disks to the sizes of class 1 disks, we could distinguish between these two scenarios for disk angular momentum transport. So let's do that. So the answer is they get bigger. So here are the class 1 disk sizes. They're about 100 AU in size, the gas disk sizes. And the class 2 disks, the Tauri disks, some are about the same size, but many are much, much larger. And these lines show the kinds of size growth that we would expect for different initial sizes of disks with different amounts of angular momentum transport efficiency. So the basic idea here is that the only way to make these disks grow with time is for disks to play some role in their own angular momentum, the solution of their own angular momentum transport problem to in-disk angular momentum transport. I'll just skip this for a moment. So here's my takeaway. That just because theorists can't figure out how something works, doesn't mean it's not happening. The observations of disk sizes strongly suggest that disks can play a role in the solution of their own angular momentum problem. How they do that, whether they're redistributing angular momentum through the magnetorotational instability or through another process like the gravitational instability, is unclear, but it seems too early to abandon the idea that disks can help themselves. Okay. So I've actually come to the end of my talk, and here are my messages. Okay, so my topic was disk spectroscopy, solids, spirals, and sizes, and here are the main messages from all of that. So we were first interested to know whether we could probe the earliest, most mysterious phases of planet formation. And I hope I was able to convince you that through spectroscopy, we are able to get a chemical fingerprint of the formation of planetesimals and protoplanets, which are sequestering oxygen beyond the snow line and driving an increase in the carbon to oxygen ratio close to the star. By looking at the reservoirs of solids in exoplanets and in disks, that suggests that planet formation begins a lot earlier than we thought, that planets are built along with stars, and that the planet formation process is very efficient. Something like 30% of the solids that are initially present in a disk actually make it into planets. And that's a big challenge, I think, for theories of planet formation. These ideas inform us a little on the interpretation of all these rings that Alma has seen in disks. It's pretty unlikely that these disks are due to just the formation of 10-centimeter size objects at a snow line. It's much more likely that they've actually formed much larger objects that could potentially be creating these rings. The spirals that we see, I think, are particularly interesting. At lunch, Trent and I were discussing what all this hot star and cold star planets stuff means. And when you think about it, you know, if you don't detect a planet, is that because the planet's not there, or because it's a lot less luminous than you were led to believe? It's hard to know. The spirals, however, are suggesting that they probably are driven by planets, that these are systems that should have some planet. And the fact that the planets are not seen, even though they're the kind we should be able to detect, they're massive, they're distant, that I think is suggesting that the models of hot star models are just wrong, and that actual planets are much less luminous. And then finally, about disk sizes, the old problem of disk angular momentum transport. Even though disk winds are the new rate, it does seem, when we actually look at the data, disks seem to be telling us that they play a role in the solution of their own angular momentum problem. So don't count them out yet. Thanks.
Yeah, so you can help me understanding something here. So my understanding was that there was one snow line, but is there more than one?
That's a good question. So yes, when we talk about the snow line in terms of planet formation, when we look at the structure of our own solar system, there are rocky planets interior and giant planets on the outside, and they're divided by the water snow line. Mm-hmm. So that's the main snow line that I think people have invoked for planet formation. And that's because the amount of water that's in the disk increases the solid mass by a factor of 2 or 3. So that's a great benefit if you want to start from solids and build planets that way. So it should be a lot easier to build planets when you have water condensed out. And so I think we actually see the effects of that. To interpret all the multiple rings in the HL Tau disk, people had to invoke other kinds of snow lines, whether it's ammonia or CO or something like that. And you might wonder, well, how much mass or how much an effect of something that's pretty a trace species like ammonia, how much could that really have? So that's a good question. I think that's one of the things that bother people about that particular scenario. But in principle, other species do have their condensation radii, and they could play some role.
So you talk a lot about the fact that we don't directly detect planets out of those distances, but what about microlensing? Does that reconcile with what you're saying, or are they should have different limits because they're not really worrying about how hot they are, right? They're not worrying about the thermal to be able to detect them. So is microlensing sort of consistent with what you're seeing now? Because a lot of the plots are from much older, where there have been a lot more microlensing detections.
Sure. So the sensitivity for microlensing is really in an intermediate separation range from 1 to 10 AU. That's for the kinds of targets that people have been looking at, that's I guess the optimum separation range where they can detect stuff. So that is smaller. But in fact, when you look at the mass budget, most of the planets that we know of, most of the solids that we know of that are in exoplanets are in this region of in the exoplanet region of that's probed by microlensing, so 1 to 10 AU. So it's a very important planet population. But if you're talking about what kinds of planets can drive the large spirals, two-armed spirals that are seen in high contrast imaging, those spirals are pretty big. They go out to tens of AUs. So the dynamical model suggests that the location of the planet is exterior to the arm. So somewhere between 30 and 300 AU. So, if microlensing is probing the 1 to 10 AU range, the spirals are pointing to planets at larger radii.
So I had a question about when you were talking about spiral structures that were most likely to be very unstable.
Yes.
So I'm not actually interested in planet formation, but I come from the galaxy side.
Yeah.
So obviously we see a lot of gravitationally stable spiral galaxies. So, and a lot of it seems to be, you see kind of some analogs, stars and galaxies can be, kilometer-sized rocks or spiral disks,
Yeah.
Debris disks. So what's the difference? What differences between these two different, size scales essentially?
Yeah.
Is causing your debris disk spirals to be supposedly unstable?
That's a good question. Okay, so there's some differences, I guess, between Tauri disks and galaxies. Not like size or anything, but so there's a central star in the Tauri situation, and not so much in the galaxy situation.
Well, we have a supermassive black hole.
Yeah.
Not the same mass ratios, but
Okay.
there's a
Pretty small mass ratio.
there's a the center, galaxies mostly is almost rotating like a solid body.
Right.
So,
Okay. So let's think about among the galaxy population, which are the ones that we know of that have terrific two-arm spirals, like M51. So M51 has beautiful spirals, and M52 is up here. So there are flocculent spirals.
so this is NGC 5194 and 5195, right? It's the interacting system, right?
Yes.
Okay.
Yes.
Just make sure I got the right one.
So I guess what I'm thinking is I'm not in galaxies, so I really can't answer your question very well. Maybe somebody else knows the answer here. But I think even in galaxies, when you see strong two-arm spiral structure, often it's due to some kind of interaction, because you have a massive perturber that's driving this two-arm structure. Does anybody know whether?
I think it might be bars also.
Okay.
I think bars can also play a big role in it, but there's also nearly barless, two-arm spirals too. So
Yeah.
or very tightly wound two-arm spirals. So, but it's
That's
just
a good question.
yeah.
Yeah. I guess I'm just thinking for the kinds of morphological things that you see in the scattered light images, the closest analogs are interacting galaxies in the galaxy population.
So actually, I study interacting galaxies. If they interact, it's the giant train wreck.
Yeah.
Usually.
So when you study interactions, under what circumstances can you get a two-arm spiral?
So I don't actually, I study, so I don't. I just get a messy system. So
Oh, okay.
it's just, everything's everywhere.
Okay.
Which makes photometry hard, but yeah.
Okay. So I guess I'm thinking that some kind of perturbation actually drives a two-arm spiral in galaxies, and that would be an analogous situation to what we have here if you have a massive companion, like,
So
a
perhaps
Jupiter
maybe it's
massive
just different
companion.
time scales then, possibly.
Maybe.
So with debris disks, you have the time scales in which you see it is a lot shorter as compared to our human lives.
Yes.
With galaxies, there's a lot more that we see, and there's going to be more of them that we see in that stage. You see, does that make sense? Maybe that explains why there's a difference.
Could be. I don't
One
know.
of the differences, I may be wrong as well, but I think one of the differences, and I think you were alluding to that, is that the stellar disks are not self-gravitating.
That is true. That is
Well,
another big
galaxies
difference.
are, so I think that's causing also different dynamical structures.
That's a really good point. Yes.
Perturbations.
So for Planet 9, a lot of us have issues with it because in terms of planet formation, it's very hard to make something as massive as that out that far.
Can you remind me what's the current idea of the mass of planet M?
Above 10, I think it's 10, or it could be, I think, 4 to 8 Earth masses around 700 AU.
Okay, yeah,
And that, although they want to, I mean, you could use pebble accretion and that you're sending things out that far.
Yeah.
A lot of dynamics have a problem with the fact that how do you put it there?
Right.
And so it seems like you also have that problem because you're putting a lot of planets outside at 200, 300, 400 AU that also now need to, while you're, also, that the outside of the disk is being irradiated as well, out at these outer regions. So is that a problem for this? Because we're sort of invoking this pebble accretion as maybe a way of sending material out there to form it.
Right.
But how to keep something that far out or even put it there seems to be a problem even for our own solar system. So how do you resolve that for this model?
yeah, that's a good question. I guess, how do people resolve it for HR 8799? 4 planets, pretty massive, at these same kinds of distances. When I hear people talk about that, they're often talking something like gravitational instability, but they're really not sure. I think those are some really interesting open questions. That's a case where we do see the planets, they're massive, they're multiple, and they're pretty far away. How do you make those kinds of systems? Maybe something similar to that is going on with the systems that are driving the 2-arm spirals. So it will be really interesting to see whether there really are planets out at those distances, because like you say, that requires disks to be more massive, more efficient to make planets at those distances. Yeah, good question. Andy.
So you mentioned at the beginning that the comet is a planetesimal.
Yes.
So how does the Oort cloud relate to everything else that you said?
Good question. Okay, so the Oort cloud is made up of comets, I believe. Of course, it's just a concept, but the Oort cloud is made up of comets. They're probably icy like the comets that we see. And they originally came from the Jupiter-Saturn region. So you can imagine that the disk that made the solar system was full of planetesimals. There were particularly icy ones in the Jupiter-Saturn region. There was a lot of jostling there, which flung them out into the Oort cloud. Megan, is that correct? Okay, so I'm still on the right track there. So I would say that's the connection, that they are the leftovers of that process.
So for your tools for protoplanetary or protostellar is the case.
Yeah.
Basically, if you think about planet or protoplanet there, is it just like one planet system? Like if you think about it, pretty close comparison should be not actually this galaxy or spirals from the planetary galaxy, but rather if you think about that IRC 10216, that asymptotic giant branch star.
Yeah.
You may have a companion, you may have a spiral pattern inside of revealing structure.
Oh.
So if you think about your true spiral case,
yeah.
If you have is it possible you have a multiple planet symbol in there?
Well, so I'm interested in what you said about 10216. I didn't know anything about the spiral connection there, but
it's not. I think it's not confirmed, but there is possibility it has some kind of spiral pattern.
Oh.
And there is a possible companion around it. Yeah.
Okay, so
is this kind of dynamically? It kind of fitting your bill, like there's a companion, there is a instability for provoking kind of spiral pattern.
Yeah, I think that's a very similar idea, because the idea for this particular situation is that you have a non-self-gravitating disk that is perturbed by a massive companion. It happens to be a planet exterior to the disk, formed probably from the disk. And it drives, because it's so massive, it drives a very strong 2-arm spiral pattern. So perhaps something similar is going on in 10216, where a companion is also doing the same thing.
So my question was like, in case your picture, there should be just only one massive planet for the systems, or is it possible it's okay to have very small minor things around, but there should be just one massive two?
Yeah, to drive the 2-arm spiral, usually it's one massive object exterior to the arms. If you had multiple planets at those kinds of distances, they would all be competing to drive those two-arm spirals, and then you wouldn't get a nice pattern.
I was wondering how well do we know masses of photoplanetary disks, and,
Such a great question.
and then how that affects this kind of theory that planets have to form earlier. Because if we're kind of order of magnitude even 3 times maybe uncertain, maybe we're this could change, right?
That's a very good question. Okay, so I think one of the most fundamental things that we don't know in planet formation are really what are the masses of disks. And so I was trying to get around that in my talk by only talking about the solids, solids in early stages and solids in planets. But really what we want to know is what is the total mass of the disk. So there are so many challenges to doing that. So if you want to measure the gas, you need to find, well, it's mostly made up of molecular hydrogen. Molecular hydrogen has very widely spaced transitions, which make it very unsuitable for probing most of the temperature that the disks are at. So that's why nobody uses it. So that's why we often look for a chemical tracer, which often is CO. But CO has its own problems. It could be dissociated. It could freeze out onto when it's cold. You have to measure the temperature of things. It could be optically thick. It's just, so there's so many things that get in the way of a very clean tracer of disk mass. I think it's just really hard, measuring gas masses directly. That's why people have been working with dust masses. So dust masses are great if you know the size of your solid distribution, but if it's growing or if it becomes optically thick, then you're a little bit out of luck. You have to work harder and measure things at different wavelengths in order to figure it out. So clearly it's, our field was really surprised by HL tau and a lot of the other rings that have been detected since, because initially all the modeling that we did to figure out what is the masses of disks assumes unevolved, small grains, smooth, optically thin, etc. Clearly it's not smooth. They could be optically thick regions. We may not be sure how big the sizes have grown. I showed you the chemical evidence that large objects have actually grown. So, you don't really know what the total amount of solids is there. So going to an even earlier stage of evolution, like class 1 disks, where less evolution has probably occurred, we're probably in a better situation there. But like you say, what if grains have already grown in the class 1 fields? Then, same situation. So, yeah, that's kind of where we are.
Is there a number you can quote for how uncertain masses of disks are?
I think disks are not so massive that they're gravitationally unstable. So that would be 300 Earth masses of solids. And we know that exoplanets have on average 20 Earth masses of solids. So, maybe like 10% of the gravitationally unstable mass is going into planets. I would say that's maybe an upper limit a lower limit on the efficiency of planet formation, 10%.
Well, let's thank Joan for a really nice one.